Good evening everyone, and welcome to today's worked exam answer video. Today I'm having a look at what could be either an AS or an A-level question looking at the dehydration of alcohols, but as well as kind of thinking about that as a reaction, and we will have a bit of a mechanism to complete on the reverse side of this question. It's also bringing in different types of formulae, different types of isomerism. So we've got position isomers, chain isomers, functional group isomers, as well as thinking about the actual dehydration of alcohols into alkenes. So there is a lot going on here. So my advice for this would be to draw things out in pencil, because then you can always rub it out. You're not going to use up all of your space. Obviously you can do it in pen and just cross through it in pen. But if you're not sure, obviously don't use the whole space, draw something and go, that's wrong, and then it just gets faffy with extra paper. So that would be one thing, and obviously I'll give you little hints and tips sort of throughout for each of the different questions. So we've got these on the front all about different isomers of pentantuol, thinking about dehydration there, and then we've got the mechanism for dehydration here. We've got to add some curly arrows onto the intermediate and name the mechanism. And then we've got to think about what an alternative product from this particular mechanism could be, which again, quite tricky. So hopefully you can stick with me, guys. If there's any questions, of course, at any point, please, as always, just let me know, leave me a comment, send me a message, send me an email, all of the usual means of communication, very much open. So when we're thinking about dehydration, I guess first and foremost, dehydration, we are going to be removing water. Now, in terms of where the atoms that give us our water molecule are going to come from, we're going to get the OH of the alcohol to leave, and then we're going to take a hydrogen from an adjacent carbon to where the OH is. So, for example, if we had something like this, we would be looking to get rid of this H here, to get rid of this OH here, and then we'd be putting the double bond between those two carbons, something along the lines of that. The alcohol that we're dealing with is pentantuol. Now, they've purposefully had to pick a fairly long-chained alcohol, because the shorter the chain, the harder it is to draw different types of isomer, but also we won't necessarily be able to get a mixture of alkene products, which is one of the things that they're asking us in part B. So we've got pentantuol, and they've also very handily there given us the molecular formula of C5H12O, which is helpful because when we're drawing isomers, if they're structural isomers, which all of them on this page are, they still have to have the same molecular formula. Well, every single type of isomer has to have the same molecular formula, so that's a nice way of us just being able to check that we've got everything that we should have in the answers that we're going to draw. Okay, so first up, we've got to draw the displayed formula of an unbranched position isomer of pentantuol that can be dehydrated to form a single alkene. There's a heck of a lot going on there for 1 mark in one question. Displayed, we've got to make sure we get the bond in between the oxygen and the hydrogen of the OH group. It's very easy to just write it as OH, and I put myself in that category as well, but displayed, it's every single bond. Unbranched position isomer, so the first thing that I would do, knowing that it's an unbranched position isomer, we're going to be moving the position of the OH group, but we want to keep the longest carbon chain as 5. So 1, 2, 3, 4, 5. Then what we might want to think about is what other options for position isomers do we even have of pentantuol. So in pentantuol, the OH group will be either on this carbon or that carbon. It wouldn't matter. They're both the same. They'd both be called pentantuol. We could move it to the end, and that would give us pentan 1ol, or we could move it into the middle, and that would give us pentan 3ol. So those are our only two position isomer options that we have, and it might just be helpful to consider what the different options are to help you narrow it down if you're getting a little bit stuck. And then the final part that's important is this dehydrated to only form a single alkene. Now, when we're looking to dehydrate, as I said up here, we need to take a hydrogen off of an adjacent carbon to where the OH is. So not in every single instance, but when we have the OH group not on the end of the chain and it's in the middle of the chain, not necessarily the middle, but not the end, we might be able to look at taking a hydrogen from an adjacent carbon to the right hand side, but we might also be able to have a look at taking a hydrogen from an adjacent carbon on the left, and that might, won't always, depending on symmetry, but that might then give us different products. Okay, so here, if I was to put my OH group on the first carbon, the only hydrogen on an adjacent carbon I could then take would be a hydrogen on carbon 2, and that would only then generate pent-1-ene as the product of this dehydration. There'd be no other possible alkene products that I could make. So making sure that I put the bond between my O and my H, so it's displayed formula, and then all the rest need to be hydrogens. And then we just need to make sure we have definitely met all of the criteria. So it's definitely unbranched because all my carbons are in a straight line, one long continuous chain. It's definitely a position isomer because we've moved the position of the OH from the second carbon to the first carbon. It's definitely displayed formula, and if we dehydrated it, we'd get an alkene where the double bond will be in there, and that's the only place a double bond could go. Perfect. So that's everything covered for the first question. Now the second question gets a little bit more annoying because we've got to do skeletal. Now please do not be afraid of drawing it as a displayed formula first, which is exactly what I'm going to do, then putting a line through it and then converting that to skeletal. If you're happy going with skeletal formula straight off the bat, wonderful, but don't put pressure on yourself to do so if that's not something you feel comfortable doing. So we've got to do skeletal. This time we're looking for a chain isomer, so we can't have all 5 carbons in a line. And this time we're looking for a chain isomer that of pentan-2-ol that can be dehydrated to form a mixture of alkenes. So this is where if we look at the carbon to the left, remove a hydrogen, we'll get a different alkene from if we look to the carbon on the right hand side. So as I said, I'm going to start with displayed formula and then I can convert it to skeletal. So if we're going for a chain isomer of pentan-2-ol, the perhaps easiest place to start would be to try 4 carbons in a line and then think about having 1 methyl group and see if that works, rather than kind of going, oh, well, maybe we should try having 2 methyl groups initially. Always kind of work logically with isomers wherever you can. So if your longest chain is initially 5, shorten it to 4 with 1 methyl, then shorten it to 3 with 2 methyls, and so on and so forth. So that the methyl is going to either have to go on the second carbon or the third carbon, because it can't go on an end, because then it's not a methyl group, it's just a part of our longest chain. When we're dealing with chain isomers, we should only be changing the length of the chain, so we should keep the alcohol group on the same carbon. So if we keep that on carbon 2, like that, we then need to have the option to take a hydrogen from the left-hand side carbon or the right-hand side carbon. So we need there to be a hydrogen there and for there to be a hydrogen there, so that we can then put the double bond in there. Or if we take the hydrogen from the right adjacent carbon, put the double bond in there. When we're then thinking about where to put our methyl group, I think we could either have that underneath the alcohol or on the other middle carbon to where the OH group is, and I think either of those would represent chain isomers of pentan-2-ol that could give us a mixture of alkenes. If we had the methyl group on the second carbon, we would then make either 2 methyl but-1-ene or if we remove this hydrogen, we would make 2-methyl butene. So 2 different products there. If we put the methyl group here, we'd still be looking to take this hydrogen here, and that would give us 3-methyl butene, or if we took this hydrogen here, we would get 2-methyl butene. So again, they're both different products, so I don't think it matters where we put the CH3. For the purposes of a nicer skeletal formula, I'm going to put the methyl group there. And obviously, this isn't going to be my final answer because we're working in skeletal for this question. So now my longest chain is 4. So remember, as soon as you put your pen on the paper, that is 1 carbon, because in skeletal there's a carbon at every end and every bend. So 1, 2, 3, 4. And then if you draw a zigzag line, just count 1, 2, 3, 4. And obviously if you've drawn too many, you can reduce it by 1. And if you've not drawn enough, you can add 1. Okay. Now, my OH is on the second carbon, and we have to draw the O and the H in our skeletal formula because the only bonds that we don't draw are between carbon and hydrogen atoms. And then the methyl on the third carbon would just be a stick down like that. So that would be the answer that I would then leave, and then obviously I'd cross through that one, which I will do just for clarification, but I'll just do it once with that pink pen like that so you can still see what I did in displayed formula. So that's part B. Now, just to complete the pack, they've then given us a question about functional group isomer. So functional group isomers are where we change the functional group so that it doesn't belong to the same homologous series anymore. The other key word here is unbranched. And notice that they haven't specified here what type of structure they want us to draw. They've just said draw the structure. So we could do that displayed formula, we can do that skeletally, it wouldn't matter. We can't draw it in sort of the structural of sort of CH3, CH2, CH2, blah, 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 because functional group isomers, my apologies, I don't know what I was thinking there. I was thinking of alkenes to cycloalkanes actually. So yeah, we could probably do it as structural formula. The functional group isomer of an alcohol, technically you won't have learnt this. So this is where this is thinking outside the box, bit of application. We know we've got to have a different homologous series that this compound's going to belong to. The only other thing we can do with our oxygen is, rather than having it bonded to 1 carbon and 1 hydrogen, is we can put the oxygen into the middle of the chain, and that technically makes it an ether. And if you've studied NMR and you're in year 13, then you will recognise ethers from some of the unknown compounds that you've been drawing or analysing in NMR questions, and you'll also recognise it from the data sheet as well. So we've got COC. That's the only thing we can do to keep the molecular formula as C5H12O. We can't start putting double bonds in to the oxygen because we wouldn't then have enough bonds to put all the hydrogens on. And then it's unbranched, so we just want all of the carbons to be in a line. So I could do 1 here and then have 4 on this side, or I don't know why, I'm just going to go with 2 and 3 instead. Just felt a bit nicer in my head. And then put all my hydrogens on. So yeah, and for anyone who is interested, that is an ether. In terms of you knowing that that's an ether, it's not really on the spec anymore. You certainly don't have to know the names of any ethers or anything like that. But like I say, you will come across lots of ethers when you have a look at NMR in year 13. Okay. Part D. Another isomer, we're still going with our isomers, so another isomer of pentanteol is an alcohol that is not dehydrated when heated with concentrated sulfuric acid, which is our catalyst. So if we can't dehydrate the alcohol, we can't take off the OH and a neighbouring hydrogen. So there can't be any neighbouring hydrogens to where the OH group is. So again, don't be afraid to, draw this in pencil first. We don't have to draw it in skeletal, it just says draw the structure. So we can do it in displayed or skeletal, or probably structural as well. I'd recommend displayed is the easiest because it's the most visual. So if we are thinking about an alcohol can't be dehydrated, the carbon with the OH group can't have a hydrogen on an adjacent carbon. So to make life easier for myself, I'm going to put the OH group on the end carbon, because then I only have to consider one adjacent carbon, which will be the one to the right, and that carbon then can't have a hydrogen on it. So we can put 2 methyl groups on there. And then if we're thinking about our C5H12O, then that means we're going to need another carbon on the end with 3 hydrogens like that. So we cannot take a hydrogen off an adjacent carbon to where the OH is, so we can't dehydrate, we can't remove a molecule of water, so we can't get a double bond in this particular compound. So that's relying on you really knowing how dehydration works to be able to, again, put that together. So not the easiest question, but hopefully you can see how I went about doing that. So let me just add here, when we're talking about not dehydrated, so a water molecule cannot be removed. Okay, so those are the sort of isomer-based dehydration questions. If we then turn over, at the top they've given us this incomplete mechanism for the dehydration of a compound. It's a pretty hideous looking compound, and they've only done that to try and put people off. Because it doesn't matter sort of what the rest of the compound is. The key thing is that we know what is either side of the carbon with the OH group. So they've done the first step, which is protonating the OH to turn it into OH2+, and then we have to complete the mechanism for this reaction by drawing 2 curly arrows onto the intermediate. So the intermediate is the one in the middle, because that's not our starting point and it's not our ending point either. We then also have to name the mechanism. Now, this is one of those examples where we have a name of a reaction and the name of the mechanism by which that reaction occurs. So dehydration occurs via elimination. We eliminate the OH as an OH2+ ion initially. When it's attached on there, we'll eliminate that, and we'll put the double bond in, and we'll have dehydration because water will be removed. So in order to do that, we're going to need to eliminate the OH2, so curly arrow from the carbon-oxygen bond to the oxygen. And then to put the double bond in, we're going to need to have the adjacent carbon to hydrogen bond, that bond getting broken and the electrons going to make the double bond between the 2 carbons, the left with the hydrogen, the right with the OH2+. And that is how we can eliminate our water. Now, looking at either the reactant or the intermediate, we can see that in this instance, to get this particular product with the double bond between those 2 carbons, it has to be this hydrogen that comes off, this bond that then goes to form the double bond between the carbons, and then obviously we're eliminating the OH2+. However, the final part of this question wants us to think about an isomer of this final product that could also be formed in the reaction. We have to draw the structure of this isomer. So again, which other hydrogen could we remove to then give us a double bond in a different place? And if we look at the carbon with the OH2+ group on it, we looked at the adjacent carbon to the left and took that hydrogen to put the double bond in this position here, but this carbon has an adjacent carbon here as well. So we could take a hydrogen off of here, break the carbon-hydrogen bond, put the double bond in there instead, and still eliminate the OH2. So in terms of drawing that, it's a pain because the compound is cyclical, and it's got all sorts of random things that make it up. So something like that, and then C6H5, and then we'd be leaving that H there, not taking that hydrogen this time. And then to this carbon, where we had the CH3 before, if we take off a hydrogen, that will then only be a CH2. That's where our double bond will be, and then the OH2 plus will be eliminated from there. So you can see how we've then got the double bond in a different position here to where we had it here. So mixture of alkene products, because we have sort of an asymmetrical alcohol in the first place. So considering previous kind of questions to this, really just focused on sort of dehydration as a process, knowing the catalyst, yes, being able to draw a mechanism, an elimination mechanism for the dehydration reaction, but this really went to town on thinking about it in a lot more detail, thinking about different types of isomers and the effect of that on the dehydration process. So yeah, not the easiest question. If anybody has any questions on my working, my answers, please, as always, get in touch. Apologies for the quite long video, but it was quite a tricky question, so thank you for bearing with me, and thank you so much for watching, guys. Hope you all have a lovely rest of your weekend, and I will catch you in a couple of days. See ya!